Welcome back, everyone. So we're going to be starting the second notes of the functions review unit, and we're going to focus on modeling with quadratic functions as well as looking at function operations. So combining functions through multiplying, dividing, adding, subtracting, and adding in a fifth operation called composition. So we'll start with modeling quadratic functions. And so these are going to be problems where we can use quadratic functions in order to identify maximum values. So our goal is to maximize some function that represents area, perimeter, volume, etc. So we'll start with number 1. So you can go ahead and read through the question. Mary wants to fence a rectangular garden to keep deer from eating her fruits and vegetables. So one side of her garden is against a fence or a shed wall. So she doesn't need to fence that side, but she does need fencing that's going to be perpendicular to the wall and parallel to the wall. And she has a total of 80 feet of fencing to use for all sides of the area that she's closing in here. So let's go ahead and see how this is going to work. So we'll just note these types of problems are typically called optimization problems. Our goal is to figure out, and optimize the area. So we want to build an area that's going to be the largest possible area with the given amount of fencing that we have. So we'll note 80 total feet is what we call a constraint. So this is our constraint. So we can't build an infinitely large wall. Fencing. We can only create this rectangular garden region with that 80 feet. So that's going to be our constraint. That's going to be what limits how large we can make the area. So now we need to figure out, how do we get quadratic functions involved? So what we'll notice here is that the three sides perpendicular are all the same length. So let's call that length x feet. And then this horizontal length, we don't know what it is, but it's definitely most likely going to be something different. So because we don't know, we'll give it a different letter. We'll call it y feet. So we've got 3 segments that are going to be the same length and one that could be the same length, but it could also be different. So we'll use what we know first, which is the perimeter. So the perimeter is just the total length of the entire gardens. So we've got 2 gardens here, and we can easily see that 3x plus y is going to give us the entire perimeter. And since we want to use everything, this is going to equal 80. So 3x plus y equals 80 is what we call the constraint equation. So this is our constraint equation. All right, so x and y are limited by that value of 80. And every optimization problem you have is going to have to figure out the constraint. So the next thing we want to do is figure out, what do we want to optimize? And we can see that we want to optimize the area. So which dimensions will maximize the total area of Mary's gardens? So the area of the region is going to be x times y, just using length times width for the area of a rectangle. So we want to optimize x times y, but obviously, right, we've got 2 variables, which makes it a little tricky. But we'll note this is the optimization equation. So what we're going to do is we're going to make this 2-variable area into a 1-variable function. And the way we're going to do that is by manipulating our constraint. So for our constraint equation off to the side here, we'll just note that if 3x plus y is equal to 80, that means y is equal to 80 minus 3x. So we're going to take that y equals 80 minus 3x and substitute it for y in our area equation. So a, which is kind of a function of 2 variables at the moment, can now be written as a of x, which will be x times 80 minus 3x, which, when we multiply that out, we can see that a of x is equal to 80x minus 3x squared. So our area is a quadratic function. And since we have a negative leading coefficient, so in front of our x squared term, we know that this quadratic is going to be opening downward, which means that the maximum is at the vertex. So this is, again, the whole usefulness of using this modeling method. So we know that the max is at the vertex for this downward facing parabola. And so we'll note that we can quickly find the x coordinate of our quadratic function by using negative b over 2a, which comes from our quadratic formula. So if x equals negative b over 2a, we'll just note that 80 is b, negative 3 is a, so we're not writing it in standard form here, so be careful with that. So we'll have negative 80 over 2 times negative 3, which gives us 40 divided by 3. So it's 40 divided by 3 feet. So it's going to be a little bit over, I think, 13 feet. So a little bit over 13 feet. And in order to find y, so we'll note we've got our first dimension here. In order to find y, we'll use our constraint equation again. So we'll bring that down here. So y is going to equal 80 minus 3 times our constraint that we just found. Sorry, our dimension that we just found. And the 40 over 3 times 3 cancels nicely, so it's just 80 minus 40, which equals 40. And you can add those dimensions together to make sure that they add up to 80 feet of fencing, and they will. So x is 40 over 3, y is equal to 40. And then you can multiply it out to get the actual square footage if you wanted to. And this is really what we're going to be doing for most of these examples. Figuring out our constraint, working with our optimization equation, and then finding those max values. So let's go ahead and go to number 2. I would recommend go ahead and pausing the video here and go ahead and give number 2 a try on your own. All right, so a farmer is using 1,800 feet of fencing to create a rectangular field and subdivide it into 2 equal-sized pens. The fence that divides the 2 pens is parallel to the field's shorter sides. What is the largest area of the field that the farmer can enclose, and what are the dimensions of the field? So definitely want to start with a picture here. So unlike the Mary's Garden problem, we are not given a picture. So we'll add in a picture here so we can see that we've got a rectangular region and we're subdividing it into 2 equal-sized pens. So it is going to look similar to Mary's situation where we've got 3 sides that are going to be parallel to each other and be perpendicular to the opposite sides. But then we've got these extra dimensions, y on bottom, but also y on top. So now we have 2 values that are unknown, 2 values of y. Again, y could be equal to x, but we're not sure yet, so we'll assume that it's different for the moment. And then we're going to do the exact same thing we just did. So we'll start with our perimeter equation, which is our constraint. So the perimeter is going to be 3x plus 2y, obviously, which equals 1,800. So we have 1,800 feet to enclose here, and we want to use all of it. So there's our constraint equation. And then our area is again going to be equal to x times y, which is nice. And so we can, that's our optimization equation. And then we can again manipulate our constraint to solve for one of the variables. And I would just typically recommend solving by y. That way you're dealing with an equation with x. So we can subtract 3x, divide by 2. And there is our new constraint value for y, which we can then substitute in. So then a is going to become a of x, which is going to be x times 900 minus 3 halves x. So a of x equals 900x minus 3 halves x squared. And we can see that we have the same situation where we're going to have a downward facing parabola that represents our areas. And so we're going to want to find the maximum at the vertex by using x equals negative b over 2a again. So we'll note b is the linear term, a is the quadratic coefficient. So we've got negative 900 over 2 times negative 3 over 2, which is going to give us negative 900 over negative 3, which is just 300. So 300 feet is going to be x, and then we can substitute that into our constraint equation. And we'll end up with 900 minus 3 halves times 300, which is going to be 450, it looks like. So 900 minus 450 is 450, and those are our two dimensions. And then what is the area of the field? We can get just by multiplying 300 by 450, 300 feet by 450 feet. So we do need to do a little bit of dimensional analysis here. And we'll end up with 135,000 feet squared, since area is going to be a two-dimensional measure. All right. So let's go ahead and head on down to the next two examples. So we've got a baseball problem and then a Norman window problem, which is an interesting one. So for number 3, I've put Mike Trout here, but feel free to put Shohei Ohtani if you want to, if you're a baseball fan, since he plays for the Angels as well, and he's a little bit more relevant these days maybe because he pitches and bats, does both, plays both sides. But we've got Mike Trout in my example. So he hits a baseball at an initial height of 3 feet from the ground. After 1 second, the ball is 67 feet high. After 3 seconds, the ball is 99 feet high. Determine a function that represents the height of a ball at a certain time t using this information. So it may be useful to maybe draw a picture, kind of to see what the situation looks like. So if we have time versus height, let's say, h of t, we know that at 0, the ball is at 3 feet. So that's going to be 0, 3. At 1 second, it's going to be 67 feet. And then at 3 seconds, it's going to be 99 feet. Okay. So the trajectory of the ball is going to follow a parabola of some kind. Now, we don't know if any of those points are the vertex. They might be, but we don't really know. But we do know that we can model this function using a quadratic function. So we're going to use standard form for this. So h of t is going to be equal to a times t squared plus b times t plus c. We're just using t instead of x since we are measuring time. So it's typical. If you want to use x for these problems, you can use x as well, but it kind of indicates that it wants us to use t. So what we're going to have to do then is simply convert these coordinates to values of our function. So let's go ahead and see what that looks like. So we'll note that h of 0 is going to be a times 0 squared plus b times 0 plus c. And h of 0 is going to equal 3. All right, so we know the function value, but we'll notice that a and b cancel out because we're multiplying by 0. So that means we actually know one of our values already for our function. So c is going to equal 3. And then for h of 1, we're going to get a times 1 squared plus b times 1. We'll, instead of putting plus c, put plus 3, since we now know what c is equal to. And that is going to equal 67. Okay. So maybe we'll simplify this a little bit. We can multiply through by 1, so we can see that a plus b plus 3 is equal to 67, or simply a plus b is equal to 64. So this is going to be our, maybe equation A, we'll call it. So I'll move over here, and we'll do the same thing for h of 3. So that's going to be a times 3 squared plus b times 3 plus 3 is equal to 99. And when we simplify that, we'll end up with 9a plus 3b. Subtracting the 3 over, we'll get 96. So we can see here we have a simple system of linear equations to solve. So you can kind of decide how you want to do that. You could do substitution or elimination. I think I will do elimination. So I'm going to take our A equation and multiply it by 3. So 3 times A is going to equal 3A plus 3B is equal to 64 times 3, which is equal to 192. So we're going to use that. And then we're going to put both of those equations together in order to solve. So let's see. We've got 3A plus 3B equals 192, and then I'll line up 9A plus 3B is equal to 96, and then I'm going to subtract. Now you might multiply maybe by -3 to make everything negative ahead of time and then add. Definitely be careful with your work. So we've got 3 minus 9 is -6A, 3B minus 3B is 0, and then 192 minus 96 is, well, 96 again. So it looks like -6A is equal to 96, which means A is equal to -16. So we can solve for A and then substitute that back in, maybe to our first equation. So we have A plus B was 64, so -16 plus B is equal to 64, which means B is equal to 80. So now we've got A, B, and C, so now we can write our model, which I'll put off to the side here. So h of t is equal to -16t squared plus 80t plus 3. And if you've taken physics, this equation might look familiar, although it's in feet, not meters. This is typically the constant for gravity in feet per second. And then we'll just note that this is going to be our initial velocity, so sometimes called V0 or V naught. And then 3 is our initial height, H0. So we end up with our standard projectile motion equation. So for number 4, we're actually going to skip that one for a moment and then come back to it, but I would highly recommend giving it a try. It's going to be very similar to the past 2 examples, or 3 examples, but going to require a little bit more work because it is a little bit messier. So we're going to get into operations of functions now. And so this is going to be where we combine functions. So up at the top, we'll just note some notational differences. Some textbooks like to write it as a combined expression. So there's this combined expression, whereas other ones like to write it as kind of a traditional object plus object, object minus object, kind of separated terms. I'm going to use both, but just note that the right-hand versions are kind of the ones that I'm going to use most often. But you might see these from time to time as well, where they put the operation in kind of a separate parentheses. So we can take functions and treat them like numbers. We can add them, subtract them, multiply them, and divide them. But what we need to be careful of is what happens to the domains as we combine functions. So the domains may not always remain the same. So let's go ahead and look at these 4. So we're given 3 functions, f, g, and h. And we're going to be doing a couple of things. So for part A, we're going to multiply f of x by 2, and h of x we're going to subtract. So what I recommend doing is just doing the substitution part first. So f of x is equal to x plus 2, so this is going to be 2 times the quantity x plus 2, minus h of x, which is this quadratic function, x squared plus 3x plus 2. And what we'll note is, for both of these functions, our domain is all real numbers. And actually, it's also true for g of x. So for all these functions, their initial domains are all real numbers. So we're going to end up with 2x plus 4 with the first expression, distributing the 2, and then I'll distribute the -1. So we'll get negative x squared minus 3x minus 2. Everything's going to become negative. And then I'll just reorganize this in standard form maybe, just to make it look a little bit nicer. So 2x minus 3x is going to equal minus 1x, and then plus 4 minus 2 is going to be plus 2. And we could leave it here as is. So that is our function in standard form. What I will note, though, is if we did factor out negative 1, we do get a factorable quadratic inside. So you could also write this in factored form. So negative quantity x plus 2 times quantity x minus 1. So any of those are perfectly fine. Doesn't matter which one you choose. And clearly, we've just combined the two polynomials with subtraction, so there's no domain issue at all. So the domain is going to remain the same. All real numbers. For b, we're going to take f and h and multiply them. And again, multiplication is not going to cause any issues either, so our domain is still going to remain all real numbers. So we'll note the domain is all real numbers. But we can get a little practice with the distributive property, right? So we'll distribute the x first, and then we'll distribute the positive 2. So we'll do blue first, and then red. So x times x squared is x cubed, plus x times 3x is 3x squared, plus x times 2 is 2x. 2 times x squared is 2x squared. 2 times 3x is 6x. And 2 times 2 is 4. So we're going to get these 6 terms, and then we can combine like terms. So x cubed is by itself, but we've got 3x squared plus 2x squared is 5x squared. 2x plus 6x is 8x. And then 4 is all by itself. So we get this 4-term cubic polynomial. But again, no restrictions, no undefined values. For part C, now we're going to be dividing h. So we'll just note this is the same as f of x over h of x. So if you want to rewrite first to kind of split the terms into a numerator and denominator, you can do that. So we'll have x plus 2 over x squared plus 3x plus 2. And now we're going to want to factor, because what we're going to worry about here is, are we dividing by 0? So we definitely don't want to be dividing by 0. So we'll note that we can factor the denominator as x plus 2 times x plus 1, which means we can determine our domain before doing any additional work. So we were going to simplify this function because clearly there's an x plus 2 in the numerator and denominator. But that x plus 2 is still excluded because either one of these values are going to give us division by 0. So we don't want either one of those values to be part of our domain. So we'll note the two values are going to be negative 2 and negative 1. So that means our domain is going to be all real numbers except those. So again, we can write that as negative infinity to negative 2, since that's the smallest value. Negative 2 to negative 1. And then negative 1 to infinity, all open because we're skipping over those two values. And then once we found the domain, now we can do our simplification. So we can cancel those two values out. So f of x over g of x is actually the function 1 over x plus 1. And you might be wondering, well, what happens when this cancels graphically? So graphically, this is going to create a hole in our graph. So there's going to be a hole at x equals negative 2. What about x plus 1? Well, x plus 1 is going to have a vertical asymptote. And again, we're going to explore these in much more detail in the next unit, so you don't need to worry about graphing these functions quite yet. All right, so for D, now we've got multiple operations going on. We're going to do f plus g over h. We need to bring g into the fight here. So g is negative 1, so we're going to have x plus 2 plus negative 1. I'm just going to do substituting in each expression first, and then we'll combine. And then we have h on the bottom again. So we can see that we get something similar to what we just got, except x plus 2 minus 1 is just x plus 1, which means we get the same domain, because we still have x plus 2 and x plus 1 in the denominator. So it's the same domain here, but we get a different outcome because x plus 1 cancels, so we end up with the function 1 over x plus 2. And we'll note that there's going to be a hole at -1 and a vertical asymptote now at -2. So these are going to be different graphs, even though we get kind of a similar breakdown of how they simplify. So these are just a couple of examples here to start on adding, subtracting, multiplying, and dividing different functions together. And again, we're going to want to keep track of the domains of those functions. Okay, so I think we'll pause here for the video, and when we come back, we'll look at function compositions, which is where we put functions inside of other functions to create new functions. So until then,